Hi, ArcfieldWeather.com meteorologist Paul Dorian here on Thursday morning, November 17th. We have an intense Great Lakes snow event coming for places like Buffalo and Watertown in the western part of New York State. I thought I'd focus in on the science behind this kind of an interesting phenomenon. It's a mesoscale event. It's hard to pinpoint the exact location of the most intense snow bands that can develop, but the winds are critically important, not only the wind speed, but the wind direction, the exact trajectory of the winds over the Great Lakes, crucial in determining where the heaviest snow bands will end up forming. And this looks like a long duration event that begins later today and goes into the upcoming weekend. First and foremost, a meteorologist focuses in on areas of upward motion, and we have a couple of reasons why we have tremendous upward motion in a typical Great Lakes snow event. First and foremost, we have frictional convergence. Now, what happens in a situation that is unfolding, such as what we have coming up here over the next 72 to 96 hours or so? You can get winds that flow over the land, and they tend to be slowed down by the frictional effects of the normal ground, with the bumps in the ground, the hills in the ground, and then that same air can flow over the open waters of Lake Erie, and it'll tend to speed up because it's a smoother surface. It's not necessarily perfectly flat, the water surface on Lake Erie or Lake Ontario, but it certainly is smoother, less friction than over land. So the air tends to increase in speed as it flows over the smoother surface of Lake Erie in this case. Then it reaches land right here and starts to slow down again, and it piles up, and that is what we call frictional convergence, that leads to upward motion as the air tends to slow down upon approaching land again. The wind speed will tend to lessen, and that convergence leads to strong upward motion, in this particular case just downstream of that wind flow. Again, the winds will actually speed up over the smoother surface of the water and then tend to slow down again as it moves back out over the rougher land surface here, leading to upward motion. Now, there is a second mechanism to lead to upward motion in a Great Lakes snow event, and that has to do with buoyancy. Basically, the lower level of the atmosphere becomes warmer than the upper level of the atmosphere, and warm air rises. As that air rises, it cools and condenses, first resulting in clouds, and if there's enough of a lift, enough upward motion, it'll eventually result in precipitation. In this particular case, we're dealing with precipitation in the form of snow bands, and they can become intense. First of all, what do we mean by buoyancy in this situation? Well, the water temperatures right now across Lake Erie, Lake Ontario, both are generally around 50 degrees, and the air that's going to move over these still relatively warm waters are in the 20s for the most part. So you have a steep lapse rate, a buoyant atmosphere that will develop later today across Lake Erie and surrounding areas, and later tonight across Lake Ontario and surrounding areas. You'll have that destabilizing lower part of the atmosphere, again with the still relatively warm waters of the Great Lakes, with very cold air, especially for this time of the year, pouring overhead. That will steepen the lapse rate, and you'll have a lot of upward motion, and that buoyant atmosphere will lead to instability in the atmosphere. So those are two factors here that lead to upward motion. Now, the wind speed and wind direction are critical here. You can see Erie is situated right here, and the best winds for Erie, the city of Erie in Pennsylvania, to get hit by snow bands will be coming from the north and west, such as drawn right here. Same thing for Rochester. The best winds for Rochester to get snow bands off of the lake will be with northwest winds. Now, notice the orientation of both Lake Erie and Lake Ontario. The longest stretch occurs from southwest to northeast, pretty much in both cases here. Just because of the geography, the wind can remain over the water longest if it's out of the southwest over Lake Erie, or maybe west-southwest over Lake Ontario. That is the longest fetch of air moving over waters as compared with, for example, northwest winds. So this kind of a wind flow is what results in intense snow for Buffalo. This kind of a wind flow is what results in intense snowfall for Watertown, New York, and indeed, that is what is on the table here from later today and later tonight all the way into the upcoming weekend. This is a perfect scenario for Buffalo to get pummeled by snow, and Watertown as well. Again, west to southwest winds produce the longest flow over the water, and that's where it picks up the moisture. When the air flows over the water, not only does the lower atmosphere become destabilized, but it becomes more and more moist, and the longer the time over the water, the more the moisture can be dumped on places like Buffalo and Watertown in this particular scenario. Again, going back to Erie and Rochester situations, notice northwest winds here and over here will indeed produce some heavy snow events for Erie and Rochester, but because of the orientation of these two lakes, you will not get quite as an intense of a snow event in Erie or Rochester as you can in Buffalo and Watertown. By that I mean, if all else is equal, let's say 48 hours of northwest winds will not produce as much snow in Erie as Rochester as west to southwest winds for 48 hours will produce in Buffalo and Watertown. Now, can you get lake effect snows when the lakes freeze over? Let's say January and February, these particular lakes are very likely to freeze over. In fact, Lake Erie happens to be the shallowest of all the lakes, so it has a high probability of freezing over. Well, the answer is yes, you can get lake effect snows even when the lakes freeze over, and that's because of the frictional convergence. Again, you can have the winds flowing over land, and they tend to slow down because of the roughness of the land. Well, if this is ice cover, that's still a little bit smoother than the land mass, so you certainly can speed up the winds again going over an ice-covered lake, and ultimately when that wind then ends up flowing over the land, it'll slow down again, and in fact you can end up with frictional convergence here even in an ice-covered situation, let's say in January and February. Now, having said that, it's liable to be much more limited in its intensity in January and February when the lakes are frozen over. First of all, the moisture is vastly inhibited because of the ice cover, and because of that, and a little bit less of a reduction in the frictional convergence compared to the water, and a little bit less of a buoyant atmosphere as compared to a pure water situation here. So yes, you can get lake effect snows in the middle of the winter, but not quite as intense as this time of the year. In fact, most of the heavy historic snow events, Buffalo, Watertown, will occur in the month of November, maybe into the first half of, let's say, December, before those lakes start to freeze over. And the freezing over of the Great Lakes and farther north, the Hudson Bay in Canada, are pretty important, very important for the winter time, especially for temperatures, let's say, south and east of the mountains across the I-95 corridor region, up and down from D.C. to New York to Boston, let's say. Ice cover on the Great Lakes will enhance the possibility of very cold air making its way from Canada to the I-95 corridor region without getting modified. You can have kind of a direct discharge of that cold air from central Canada moving over the frozen Hudson Bay or the frozen Great Lakes into the Mid-Atlantic region, into the Northeast U.S. So it certainly is something that we closely monitor. And with this kind of a cold pattern over the next week or so, you certainly can perhaps have ice starting to form in the Great Lakes maybe a few weeks earlier than normal this particular season. Well, let's now go through the evening run of the NAM model. This is the 12-kilometer version of the NAM model from 06Z. And first I want to start off with the winds, the wind speed and the wind direction here over the Great Lakes. This is beginning the day here on Thursday morning. Here we are, Lake Erie. Remember, Buffalo right in this region right here, Lake Ontario and Watertown right here. Let's move through on an hourly basis and watch what happens to the wind flow here. First of all, the greens represent higher wind speeds as compared with the blue here. So you can see the winds are kind of increasing over Lake Ontario by later on this afternoon. And then later on this evening, look at the wind increase in speed over Lake Erie. And then by the time we get to late tonight and early tomorrow morning, you can see the wind speed increases over Lake Ontario at this particular time. Now, we have wind barbs, and the way to read these wind barbs, if you see a wind barb like this, and a couple of long lines, let's say like this, and a shorter line like this, what this means is the wind direction is right in this fashion, in this particular case, southwest to northeast. Meanwhile, the wind speed is indicated by these lines here. Each long line represents about 10 miles per hour and a shorter line 5 miles per hour. So this particular wind barb is about a 25 mile per hour wind from the southwest to the northeast. So watch over here, Lake Erie. Notice the wind barbs are showing the wind right in this fashion over Lake Erie at this particular time at a high speed too compared to localized areas. That leads to that convergence right here. It allows for the longest fetch of time for air to flow over the water. That increases the buoyancy, it increases the moisture. You end up with heavy snow, perhaps on the order of 2, 3, 4 feet, maybe even 5 feet over the next few days in Buffalo. Meanwhile, same sort of thing. Look at the wind flow here over Lake Ontario, west to west-southwest. That's the longest fetch possible because of the orientation of the lake, and that will allow for a tremendous upward motion right here in Watertown, in and around Watertown, heavy snow bands right here. So again, these winds will be a perfect setup for intense snowfall, perhaps hourly rates of 4 inches or so. Buffalo, Watertown. This is not an intense snow event coming to Erie and Rochester. They will get certainly a snow accumulation, but because of this kind of an orientation, the real threat areas are Buffalo, here just to the north and east of Lake Erie, and Watertown just to the north and east of Lake Ontario. Now, adding to the possibility of some historic type snowfall for these kind of places like Buffalo and Watertown is the fact that we have multiple waves of energy in the upper part of the atmosphere that will roll through over the next 72 to 96 hours or so, and multiple cold air shots coming in from the northwest to the southeast. In other words, that cold air will flow over the still relatively warm waters of the Great Lakes around 50 degrees or so for the next 3 or 4 days or so. And that is a long duration event, allowing for just a piling up of snow. Here we are beginning the day on Thursday. We have kind of a short wave here, another short wave here, and another short wave here as we begin the day here on Wednesday. Now let's just move forward here. Again, this is using the 6Z run of the NAM model. These just come rotating around, and each one of these adds to the upward motion, adds to the lift in the atmosphere over the Great Lakes, and adds to the moisture. Here's another incoming wave by this evening, and another one right on its heels, and we just keep moving forward here, now into Friday afternoon, and now into Saturday. And look at this, by the time we get to Sunday morning, maybe the mother of all the waves in this particular scenario comes through Saturday night into Sunday morning. So again, a long duration event with multiple short waves passing through from the west or northwest to the east and southeast over the next 72 to 96 hours or so increases the chance for several feet of snow in some of these favored locations like Buffalo and Watertown. Well, one last set of maps here, the 850 millibar temperature anomalies. Those previous maps were the 500 millibar height anomalies. And here we are beginning the day on Thursday. Remember I said we have reinforcing short waves of energy coming through? Well, we have reinforcing very cold air masses for this time of the year. Cold air in place way below normal throughout much of the nation that is experiencing this widespread cold wave for the middle part of November. Let's move ahead in time from Thursday morning and look at this. This is even colder than what we've been experiencing over the last few days in the central and eastern U.S. It just adds to the misery coming to the Great Lakes here. We just have reinforcing air mass after reinforcing air mass, reinforcing shortwave after shortwave, and here we go. By the time we get to Sunday morning, associated with that deep upper level trough will be a very, very cold air mass, probably high temperatures in the mid-30s in places like D.C., Philadelphia, New York City, some 15 to 20 degrees below normal for this time of the year come Sunday afternoon. That'll probably be the core of the coldest air over the mid-Atlantic region. And again, a long duration and an intense Great Lakes snow event. Looks like the biggest threat zones will be in and around Buffalo, in and around Watertown. Perfect scenario for heavy snow bands to pummel those particular areas, given the expectation of the wind speed and wind direction over the next 3 or 4 days or so. That's it for now. For ArcfieldWeather.com, I'm meteorologist Paul Dorian.